Hello and welcome back to Calculus 1 Exam 2 review. Exam 2 is on Chapter 3. I hope that you are working on your quizzes. If you haven't done any quizzes yet, that means you missed one or two. One only, right? One is due tonight, so okay. 10 problems and hour 20 minutes. I could have just written 80 minutes. There you go. 80 minutes plus the break if you need extra time, and you might be interested on what's on it. Well, calculus. The chapter is on derivatives, so we start with limit, definition of the derivative, and that's your limit. H goes to 0, f of x plus h minus f of x over h, if you forgot. Number 2, take basic limit. Constant, well, that's a 0. Polynomial, exponential, log, trig. So these are all the basic ones. Number 3, product and quotient. Number 4, chain rule. Number 5, implicit, differentiation. Number 6, logarithmic, differentiation. Number 7, rates of change. Number 8, related rates. These two together are word problems. And finally, in red, number 9, tangent line problems. Problem here. Problem, and S in parentheses. Computer science deals with those issues. So tangent line problems. And the derivative within the tangent line. We had a special lecture on tangent lines. The procedure to get the tangent line is get the slope by calculating point in the derivative, get the y value for the function, get the b because now you have xm and y, and then just write the equation and win, right? So you know the procedure. What is so what's so special about tangent line? Well, first of all, it's most important concept of Calc 1 because it measures the change, instantaneous change, and that's what the Calculus 1 is about. But the derivative on the line 1, step 1, assumes every section. Your derivative could be chain rule, product rule, quotient rule, basic. Right? So I can ask for a tangent line on sine function. Hey, derivative of sine is cosine. That's basic. Derivative on e to the x. Great. Derivative of e to the x is e to the x. Or could be implicit differentiation or the product rule. In which case, so when I have the tangent line problem, a derivative for that tangent line will be one of the anything from the list. Clearly you will see all of these on the test. Rate of Klein? What is rate of Klein? Rate of change. Rate of Klein? There we go, look at that. Change, right? Rate of Klein. So for rate of change, we had those velocity problems. I give you position function and I ask you to come up with the velocity by differentiation. And then acceleration function, again differentiation, it's the second derivative. And then I ask you what is the speed at t equals 2 seconds. You just plug in 2 in the velocity function, right? You come up with the speed. So those are the rates of change problem. And then we had the business problem. If you remember, we did the marginal cost and that stuff. So those are the two, contenders. And we also had the change in population, right? That was another one, change in population. So we said we added so many people, right, in a year, or rabbits, whatever. Now, related rates. Related rates, remember that we had the discussion about the volume formulas, where we categorized all the volume formulas into 3 groups, right? The prism ones, the spiky ones, and the sphere. So it's going to be something from there. I tend not to put the cone because cone takes forever. But guys, anything that has to do with a box, which is a rectangle, or a cube, which is right, all sides are the same, or you can deal with a ball, right? That's another one. Then we had the cool problems with triangles. All types of triangle problems, right? We had Pythagorean Theorem. Pythagorean Theorem was used to figure out those 2 airplanes coming into the airport from 2 different angles. So Pythagorean Theorem was there. We also used the distance formula, bug on a parabola, and another bug on a parabola, and the 2 problems back to back. Those were the ones that were worked out. So whatever is taking more than 17 pages, obviously, right, is not good for the exam that it's, right? So something that is short, to the point, be careful, right? Your formulas, for instance, for circles and spheres, they formulas have radius. If I give the diameter, that just means I'm a terrible human being, right? Diameter is twice the radius, so you will have to extract the radius first and then go and do your problem. What else is there? Well, that's it. If you can do the limit definition, right, with the f of x plus h minus f of x over h, we did a lot of those calculations in 3.1 and 2.3. So that's where you find a whole bunch of these exercises in those lectures. So if you go back to notes or the video, number 1 over here would be in 2.3, which is the chapter on limits, and then 3.1, which is chapter on derivatives. Section on limits and section derivatives. These are the sections that have a lot of these problems done. And then you can watch the videos. I know I did in class at least 5-6 examples. 1 over x, square root of x squared plus x minus 10, right? So now the cool part about that is when I ask you, not if, but when, I ask you to use the limit definition of the derivative to, I don't know, solve x cubed plus 7x, you already know the answer, right? You know that you're aiming for 3x squared plus 7. Because you can take the derivative using the cool methods, right? The shortcut methods, which is the rest of the chapter. So don't just leave whatever. Try to fix it, up to the point where you get full credit on that one. Product and quotient rules. If the problem says use the product rule to solve a problem, please don't go and say, I'm going to do logarithmic differentiation everywhere. Because it's education, right? So you gotta know it all for the test, and then you're gonna just forget it tomorrow. So product and quotient rule. How many formulas you have in this chapter? Like 5,000. There is a formula that the derivative of constant is 0, formula for polynomial n to the n minus 1. E to the x is e to the x. Log is f prime over f, right? Trig functions, sine, cosine. Inverse trig. We have the two very important formulas that you should know, the sine and tangent. I mean inverse sine and inverse tangent, right? Those are the important ones. Implicit differentiation, right? You take the derivative, you follow by the chain if the variables don't match. And, that's the story of it. It's just literally everything we covered. And I hope you guys, in chapter 3, and I hope you guys understand that the tangent line problem kind of overarches the entire chapter. You can find the tangent line. In 3.1, we found tangent line using limit. And then later, we are always able to find the tangent line. As soon as you can take the derivative, you can find the tangent line, including implicit. Do you have any questions, concerns, problems that you would like me to work out now? Yes.
I don't have a specific problem, but could you go over a hard using the logarithmic way to get the derivative using ln?
Okay.
Could we go over one of those examples?
Sure. There's a book right there.
Yeah.
Or you have the book right there. Oh.
I have the book.
Yeah. Okay. Yeah. See, it's called exercise, right? So, anyone so this is going to be a logarithmic differentiation problem, and we are going to go through all the steps. I'm not just going to write out the answer. We want to go and see the ln at work, right? With a smile.
Number 77, or actually number 80. Number 80.
What page you're on?
216.
216, and problem 80.
Yeah.
216. Excellent. Find the derivative of tangent to the 10x divided by 5x plus 3, everything raised to the 6th power. Awesome. So we write it as y equals, leave some space, tangent to the 10x divided by 5x plus 3 raised to the 6th power, and then we ln both sides. The next step is to expand everything using the ln formulas. So we have 10 ln tangent x minus 6 ln of 5x plus 3. So the 5x plus 3 to the 6 is in denominator, which is why it gets the minus. And the other tangent was in the numerator, which is why it gets a plus. You can have multiple ones in the numerator, they will all have pluses. And you can have multiple ones in denominator, and they all get minuses. Right, so it doesn't matter that it's x times, right? Each individual one is in denominator, so I will get minus. So now that I have this, I get to differentiate in respect to x, and derivative of ln y is going to be 1 over y, and I have to follow with the dy dx chain because I took derivative of y in respect to x. Now, going forward, differentiating each one of these is a joke because you copy the constant, you put the argument of ln as a function in denominator, and then its derivative on top. Derivative of tangent is secant squared x. Very good. Now I have minus 6, and I put 5x plus 3 in denominator, and its derivative upstairs, right? So now I have dy dx, and I am moving this y, which was in denominator, to the other side, and that y was the original function that I was looking for. So I'll copy that in. And now that is times, and I have 10 times secant squared x over tangent x minus 30 divided by 5x plus 3. And we walk away. That's it. Bueno?
Yeah.
Good. Any other questions, concerns, problems? Headache is kicking in, huh? Which one? Number 28. Baseball runners. Okay. Luckily they provided a picture, otherwise I would have no clue. Runners stand at the first and the second base in a baseball game. See? It's important to say it's a baseball game, right? This is 3.11. So at the moment the ball is hit, the runner at the first base runs to the second base at 18 feet per second. Simultaneously, the runner on the second runs to the third base at 20 feet per second. How fast is the distance between the runners changing 1 second after the ball is hit? The distance between consecutive bases is 90 feet, and the baseline at the corner of the square. Nice, thank you. Yeah, at this point, if you're wondering if I know the rules of baseball and what it is, I don't. So I went and I saw one game, it was painful, and I never looked back.
You didn't go with the right person.
What happened?
I said you didn't go with the right person.
There was about 30 of us there.
Well, how'd you not have fun then?
Oh, that's because this is crooked.
Did you have a beer at least?
It did not help. I actually don't like beer. I was way too young when I tried it, and it was bad at that time, and it's still bad now. Home plate. There we go. First base, second base, third base. "90 feet over here, 90 feet over here, right angle there." So we're going to have a player. This is the same as those airplanes. There's a player that is going to go this way, there's a player that's going to go that way. we can observe the distance between two players. So I'm just going to draw like random position for these players so that I can draw the triangle, because this is the capital distance D that we care about. So now there is a 90-degree angle at the second base, and I'm just going to draw this triangle again on the side. And show that this is exactly the same as what we had previously. We have this point going this way, and then this point going that way. Big distance D, this is X, or this is X, this is Y. And we can just go from there. So there are some cool calculations that we can do here to figure out the values, but before we do that, do we all understand that x squared plus y squared equals to d squared? And right, that's a Pythagorean theorem in a right triangle. And then I'm going to differentiate that in respect to time so that I can get speeds. So I have 2x dx dt plus 2y dy dt is equal to 2d dd dt. All of these 2's die. There we go. And now I have my related rates equation. Now they gave me speeds. I labeled my so this is my dx dt speed. It's the guy running from second to third. And then there is the dy dt speed, which is the speed of the guy who's running from first to second. And then there is dd dt, which is the change in distance between them. Thank you. So now I just need numbers. So if I read over here, it says at the moment the ball is hit, the runner at the first base runs to second base at 18 feet per second. That's going to be this guy over here. 18 feet per second is the one who's running. So that's my dy dt. So dy dt is equal to 18 feet per second. That's given. The other guy is running at 20. And that's my dx dt. dx dt is running at 20 feet per second. If you think they're running too fast, release some tigers, see them run even faster. You'd be amazed how fast they can run. So now what's left for me? Well, I have these two pieces of information. They are looking for dd dt, so I'll consider that as something that I know. I need x, I need y, and I need capital D. I can't compute this problem until I have those as numbers. Now see, the key information here is that how fast the distance is changing 1 second after the ball was hit. Now, how far do you go? How far do you go if you're running 18 feet per second in 1 second? You go 18 feet, right? So the y covered 18 feet. So how much is left in the triangle? You see, the y came from here, right? This is where the this is where the guy was standing on the first base. When the ball was hit, 1 second later, he covered 18 feet. Out of 90 feet, how many feet are left? 72 feet. So that's the number in your triangle. Your y is 72 feet. The same is happening with x. This guy is running faster, so he covered 20. Do I use 20 or I'm using 70?
20.
I'm using 20. Look at the triangle, right? So I'm using 72 and I'm using 20 because, see, the second guy was here running this way, so in 1 second he's actually running along the edge that I need in my triangle. The other guy was running at the side that I don't need, so the rest of the triangle is 72, which is to be covered. And now I can use those pieces of information in the Pythagorean theorem to figure out the capital D. So I have 20 squared plus 72 squared is equal to big D squared. It's 400 plus, now get the abacus going, 72 squared is 5,184, so plus 400, square root of the answer to get D to be 74.7 feet. Remember, 1 decimal place extra because your input numbers did not have decimal places at all. So you're allowed to have 1 decimal. And now I finally have all the numbers. X dx dt plus y dy dt is equal to d dd dt. We plug everything in. What's x? 20. X is 20 times 20 plus 72 times 18 is equal to 74.7 times the dt, which is what we're looking for. Done. Cool, right? Maybe. We don't know. So what do we have over here? 400 plus 72 times 18 divided by 74.7. The distance is changing at 22.7. So dd dt is 22.7 feet per second. That's the speed of them going apart. Does it make sense to be larger? Right? Because one is slower, one is faster. Right? So the distance between them. Remember, if you are going faster than someone else and that one is, right, you're going at an angle, right? The speed between you is going to be picking up because the other one is going slower, right? And you're going further apart in distance. Good. Happy? Moderately? A lot? Well. All right, good. Anything else? No? All right.